Hello everybody. In this video, I will be teaching on recurrent neural networks, RNNs. So now, I would like to start off by giving examples, real practical examples of RNNs being used today. And one very popular example is the next word prediction. So if you have a phone and you're typing a text and you see that, oh, it's suggesting the next word for you. That is RNN at work. Also, you might have heard of the popular stock trend prediction RNNs, and I'll tell you the different parts or types of the RNN architectures that help with forecasting stock prices or even forecasting in general, forecasting maybe daily sales of a store, weekly or monthly electricity usage, etc. And another is language translation. So early versions of tools like Google Translate used RNNs. Then after they used it for a while, they discovered a better approach to using neural networks for translations, and that will be the topic for next week, not this week. So early versions of tools like Google Translate used RNNs. So let's move to the next one. Sequential data. From the word sequential, sequence, data in sequence, where order matters. One comes before the other, and like that, and on and on. That is, there is a relationship between the data points. Examples in a book. First, you have the letters that make up the words, and the words make up a sentence, and the sentence make up a paragraph, and the paragraphs make up chapters. Chapters then make up the book. That it follows a logical order. It follows a sequence. Same with financial time series. Daily, weekly, monthly, yearly closing price of Apple stock, for example. Handwriting. Music recordings. To mention there are lots, but I'm just highlighting these few examples. So, why exactly am I talking about sequential data? Follow me. So, RNNs, recurrent neural networks, are neural networks that are designed to handle sequential data. It processes sequences, like as you can see, by iterating through the sequence elements, and it maintains something called a state. So let me give you an analogy. So for example, as you're listening to me, your brain is picking up what I'm saying word for word and following me as I'm saying it. And as your brain is following and tracking with me on what I'm saying or teaching, it is keeping a residue of what I've said previously. So that's how RNN works. The state is like a little memory that keeps what it has seen so far as it keeps going through the various sequences. Oh, I've already even started to talk about what a state is, but let's read the definition I have here. So a state represents the current condition of a system, in our case, of a neural network, plus any other information that it needs to remember. So in deep learning, which is what we are concerned here, we implement this process in a recurrent cell or a recurrent neural cell. Track with me, stay with me. In the next slide, I'll explain what a recurrent neural cell or recurrent cell is. From the diagram to your left, which I hand drew, this is a typical recurrent neural cell or recurrent cell? So let me explain. It receives, so if we're using example of text generation now, word by word or letters by letter. So let's use word by word. So the cell receives an input of a word. It generates its prediction of what should be the next word after it. That is the output. So whilst it gives that output, it saves the fact that it received a word and this was the output, but it doesn't just immediately put it inside state. It puts it in that black box called a delay. So this delay, it signifies the fact that whatever is in the state does not immediately get used until it is needed. And so it receives the next word and then it gets the delay. The delay is like a little memory. It gets the information in that delay and puts it in state. And the state goes on and updates again to the little memory, which is the delay. And like that, as that's why it's called recurrent. It happens in repetition, in sequence. As it receives the first sequence, it saves it in state that this is what happened, these are the information I received, this is the information I gave out. Okay, then the next input it receives said, okay, after the first input I received this second input, so this second input also, this is what I gave as the output. Then the third input, it saves it again, so it saves the first information, the second, the third, like that and like that. So we often place a recurrent cell on a layer of its own and call that layer recurrent layer. And a network dominated by recurrent layers is called a recurrent neural network. All right, so let's look at an example to see how exactly neural cells work. Of course, I've already touched on it in the previous slide, but this would help it drive the point home. So let's see a recurrent cell. Let's see how a recurrent cell might predict the next word of a 4-word sequence. So this is the diagram that I hand drew. Now let's start with the circle to your left. This circle signifies the initial state. And of course, because this is the initial state, it's going to be empty, full of all zeros, zero vector. And so it goes and begins. The first input is I. Remember, we wanted it to predict the next word of a 4-word sequence. So when I give it the first input I, the recurrent neural cell predicts that M should be the next word. But because we are only interested in the words that come after the 4th word, we ignore it. But the recurrent neural cells saves this information in the state that I received a word called I, and this was my output. Okay, so now let me move to the next one. So that's what's going on within the cell. So the next one receives the second word, the second input, which is love. It outputs you, saves it to the state, but still we're not concerned about that until we have the 4th word. Then after the 4th word, we are concerned about what it now begins to predict. So ignore it, but it saves this to the state. And next, it receives the 3rd input, which is deep, and its prediction is neural, but we still do not care yet. And then it receives the 4th word, learning, And remember, we're interested in what it will predict, the next word it will predict after a full word sequence. So after our fourth word, which is learning, it predicts model. And so we're like, okay, that's what we're interested in. And so why we do that is, like, why we give it time to learn. For example, after like 6 words, 40 words, 40 characters, is to ensure to help it learn. Because as we ignore the initial predictions and it continues to learn, it's able to understand the context better and say, okay, from my initial states, from my previous states rather, seems like this word models would be a better fit to any other word I would predict. So let me give it model. So it's good to at least let the recurrent network learn for a bit before it starts to predict, especially when training. Let's go to the next slide. So let's tie all of this together. Training a recurrent neural network. Recurrent neural network encompasses, if you remember, a recurrent neural cell, which is placed in a layer of its own. And let me backtrack here. And a network dominated by recurrent layers is a recurrent neural network. Good. So, like as we said, we gave our network 4 words of inputs, and then we compute an error by comparing its final prediction, which is models here, as you can see, to your topmost right, by comparing it with what we actually had in mind. That is, with the actual next word in the training data. And if the prediction is wrong, that if the word should not have been models, then the network runs backpropagation and optimization to adjust its weights and biases. Now, recurrent neural networks uses a variant of backpropagation called BPTT, that is backpropagation through time. Now, there are limitations of this simple RNN because what we've been talking about is the simple RNN. It struggles to retain information from inputs seen many time steps before. So each input in the sequential data is a time step or a token. And this is caused by the vanishing gradient problem. What is the vanishing gradient problem? It means that when the gradient becomes very small, learning slows down. And if the gradient becomes 0, learning stops entirely. But there is hope. There are 2 variants of simple RNN that helps us resolve this issue. And they are the long short-term memory, LSTM for short, and the gated recurrent unit, GRU for short. Let's look into them. So this LSTM avoids the vanishing gradient problem by introducing a method to carry information across many time steps, across many data points. That's exactly what time steps mean. Now, the LSTM has 3 internal gates: forget gate, input gate, and the output gate. The forget gate, as the name suggests, removes unneeded or unwanted information from the state. Input gates insert new information that the cell would like to remember. And the output gates select which version of the internal state to use as the cell's output. Similarly to simple RNN, you can place this LSTM cell on a layer and train it using backpropagation through time, BPTT, and optimization. Now to gated recurrent unit. GRU is similar to LSTM, but simpler and more efficient. It has just two internal gates, the update gate and the reset gate. So the update gate decides how much of the previous state to keep and how much to update. The reset gate decides how much of the previous state to forget. Now, sequence to sequence, that's what it means, sequence to sequence. It's written as this short form. Sequence to sequence is a neural network architecture, of course, that uses two RNNs, an encoder and a decoder. I'll explain those in a second. To transform one sequence to another. So let me explain. So so far with simple RNN, LSTM, and GRU, which are improvements or variants of the simple RNN, they deal with word or characters. Characters meaning letters. A, what should be the next letter after that? For example, unlike that, you keep generating the next one, After this, what should it be? What should it be? That's autoregression. I'll explain autoregression in a minute. But the sequence to sequence helps solve problems where, for example, in language translation, I want to translate "it is good" in English to French. In English, I say "it is good." In French, it could be, so "it is good." That's three words. And I want to translate to French. In French, it could be "il est très bien." Now that's 4 words. So we see that the word for word translation cannot work in language translations because in one language, a sentence can be just 3 words that convey something, but translating it into another language could be like 6 words. So this sequence to sequence help with translating sentence by sentence, as sequence by sequence. Is ideal for tasks where input and output sequences differ in length and structure. For example, as I've spoken, language translation and text summarization. So, with this pretty diagram that I drew, let's see how the sequence to sequence architecture works. I already said the key idea behind sequence to sequence is that it uses 2 RNNs, the encoder and the decoder. So the first box to your left is the encoder. It starts with the circle there, means the initial state, which is empty, all zeros, because there's nothing there, right? It's initial, so yeah. So it receives the first input. But in a sequence to sequence architecture, we are not concerned about the output prediction for words. We don't care about that because it's just an encoder, right? So that's why the outputs are just this cancel signs. So as I explained there, so it processes the input sequence and creates a context vector. Now this context vector basically holds every single information that this encoder has learned, starting from the input, from the very first input to the last input. So it carries all of this information and it gives it to the decoder. Now the decoder starts with a special token and is usually commonly written as start. And then when it starts, it then begins to generate word for word. As you see, LLBM, word for word, using auto-regression technique. And then when it's done, it uses another special token that says and. I hope you understand that. Let's go on. So I just quickly want to, I thought to include auto-regression to drive home the point even more. So what is auto-regression? Auto-regression is a technique where a model uses its previous outputs as inputs for predicting future steps. So for example, going back to this slide, the decoder uses the context vector as an input, then uses, the auto-regression technique to predict word for word the translation of what it got from the encoder, which is it is good. So in RNNs, this includes simple RNNs and its variants such as LSTM and GRU, predicts one word at a time. The output becomes the next input, and like that, and like that. The output becomes the next input, and the output of that input becomes the next input, and that goes on and on. It's also used in sequence to sequence, as the decoder generates each word based on the context vector received from the encoder, and its previous output is used as input in the next time step, as in the next data point, sequential data point. Finally, let's talk about or highlight the limitation of sequence to sequence. So this context vector, which is basically the final hidden state of the encoder, is the only information passed to the decoder. And this leads to what is called a long-term dependency problem. Because many times the context vector might have lost some information that it receives, especially when it's a long sequence of time steps of data. Also, long or complex inputs can contain more information than the context vector can store. So no matter how much you try to increase the memory of the context vector, it can anytime come across input sequences that are too much or longer than it can take. And another thing is it ignores all other encoder states except the last. And there could be pretty important details that it could have lost out on, or it could have left out in the process of all of these long time steps. And so this is where a favorite topic, attention mechanism transformers, come into play. And that would be our next video. Thank you, and let me know if you have any questions. See you next week. Bye. So real quick everyone, I just want to tell you about something exciting. My new book titled AI Machine Learning Deep Learning from Novice to Pro is available for pre-order. It will be out 9th of August 2025. And if you're my fellow crisp paper feelers, it will be out on the 9th of August, and you can order your hardcover on that same day. If you're new to AI or you already have some foundational knowledge in AI, this book is for you. From novice to pro, it doesn't matter your level, this book is for you. Okay then, let me allow you to go right back into the podcast. Thank you.